Right, so now we're going to finish up with the functional groups. So the next set of functional groups are very similar to each other, so I'm going to talk about them together. We've got the aldehydes and the ketones. So I know it sounds like a band, right? The aldehydes are up here. So the rest of the hydrocarbon is out this way, and the ketone is this, I'm sorry, the aldehyde, ketones down there. The aldehyde is this oxygen that's double bonded to the carbon and the hydrogen here. And so molecules that have this group attached to them are going to be the aldehyde group. And the simplest form of the aldehydes is formaldehyde. And I'm guessing you've heard of that one. It's the one that's the best known out of the aldehydes. It is soluble in water, and that is actually a common property for the aldehydes. This right here, this oxygen and hydrogen end on the hydrocarbon molecule makes this soluble in water because this area is polar. If you remember for our earlier videos, oxygen is greedy, it loves electrons, and so it makes this section just a little bit negative, and so it's going to be attracted to the hydrogen part of water. So these guys are going to be able to dissolve in water. And what do we use formaldehyde for? Yeah, we use it for preservation and embalming. So the biggest thing that it might relate to some of you as far as your field and study is the preservation of biological specimens. So we make a 40% solution of formaldehyde that's called formalin, and it is what's used in embalming, but we also use it to preserve biological specimens. And so this is what we use if you've ever smelled an older specimen of any sort of dead organism that's in one of those jars. It is preserved in this formalin, and it's really good at fixing tissues. That means that it keeps the tissues pretty much in the same shape and form that they were at the time that the organism was preserved, and it keeps them from degrading any farther. So that way you can study them for a longer period of time. There's also new procedures that tie both formalin and plasticization, which is injecting plastics into tissues so that we can preserve them for longer periods of time as well. And there's some really interesting exhibits that are actually out there so that you can see things like human form, but also different organisms up close. So you can see like muscle, makeup, and so forth without having to work with actual dead tissue or something like that. All of the aldehydes have an odor to them, so if you've ever experienced the odor of one of these preserved specimens, they are quite smelly. And there are other aldehydes as well. So the smells of these guys, lemons, cinnamon, almonds, and vanilla, are all responsible, aldehydes are all responsible for them. So if you look down here, this molecule is called citral. That's the one that's responsible for making lemons smell the way that they do. The next one we have here, I cannot, wait, that one is, I could just barely read it. Cinnamon aldehyde. I know. I bet that one's the one that smells like cinnamon. Yeah, that's the chemical that you find in cinnamon that gives cinnamon that odor that's very distinctive for cinnamon. Benzaldehyde, this is the one that makes almonds have that distinctive almond smell. I mean, if you try to describe what an almond smells like, it smells like almonds, right? So it's because of this guy right here. And then vanillin, this is an aldehyde that is found in vanilla, in the vanilla orchid beans. And so it's going to make that smell as we associate with vanilla. And you can see, excuse me, all of them but citral have those aromatic hydrocarbon rings, but they all have the aldehyde right there on it. So the aldehyde is the big part of these guys that have that odor to them. All right, the next one is ketones. So ketones, you can see down here. So they have hydrocarbons with an oxygen, a double bonded oxygen. So similar to aldehydes, it's just they only have the double bonded oxygen, not the additional hydrogen. And the simplest version of the ketones, and the one that you're most familiar with, is acetone. And what do we use acetone for? Yeah, it's a paint remover. So it's used to remove paint, to remove nail polish. I've actually found that sometimes it works to remove like Sharpie marker because it is a solvent. So it can be used to dissolve things that, you know, water wouldn't necessarily dissolve. All right, next group are the organic acids. Move my face off the ants. So organic acids, these guys are commonly known as organic acids, but chemically they are the carboxylic acids. And this is because they have this group attached to them. It looks very similar to the aldehyde. So it has the double bonded oxygen up here, but it has a hydroxyl group, an OH group down here. And so got a little bit extra on it versus what we saw in the aldehydes. And this alters how it works. It actually makes it acidic because this hydrogen right here pops off. And remember in previous videos, we talked about if something donates a hydrogen, it makes it acidic. And that's exactly what these guys do. The simplest of the organic acids, or carboxylic acids, was distilled from ants the first time. I know. It's called formic acid, and you can see it right here. So you've got the double bonded oxygen with the oxygen and hydrogen on the carbon, and then the only other thing that's there is another hydrogen. Super simple. The thing is that you've probably experienced formic acid because formic acid is found in the stings of bees and ants, and there's some plants that use it as well. So it's that thing that causes the stinging or the burning. So if you've ever been stung by a bee, the thing that made it burn is formic acid. It's used as a defense in a lot of insects. And like I said, a couple of plants as well. So, and that makes sense. It's easy to build, not very expensive. So there are other organic acids that you know. So acetic acid, I'm going to have to keep moving my face around. Here, I'll put myself under the pickles. Organic acid is going to form when ethanol oxidizes. So when ethanol is going to react with oxygen, you get acetic acid. And you might go, okay, so what does that do? Well, this is what creates the acid in vinegar. So vinegar is acetic acid. In fact, if you look at the label on vinegar, it will tell you what the percentage of acetic acid is. And the higher the amount of acetic acid, the more sour that vinegar is going to taste. And this is why wine can go sour or go bad. If you've ever had wine that has gone sour or gone bad, it's because the ethanol, the alcohol in that wine has been exposed to air, exposed to oxygen, and has undergone this reaction to convert from alcohol to acetic acid. And so that's why it gets that sour taste to it. Citric acid is also an organic acid, and you find it in fruits like, and if you say citrus, So yeah, things like lemons and limes and oranges and grapefruits, they all are going to contain citric acid. Lactic acid, this guy is going to be found in sour milk, so when milk goes bad. But we also will get it to purposely form to be able to create buttermilk. Sauerkraut is sour because of lactic acid that we allow bacteria basically to create, and pickles. So that's what creates that bite, that plus vinegar, because you do add vinegar to pickles. And the other big thing that organic acids are important for is they use them for raw materials for making different types of fabric, film, paints. These are incredibly useful, and some of them are also used sometimes as fixers to set some of these materials. So organic acids are incredibly important. Not only that, many of you have probably used one of them and you may not have even realized it. So salicylic acid is an organic acid that's found in the bark of willow trees, these guys back here. And this, for a long time, by a lot of different groups of people around the world, had brewed this for its fever reduction and pain-killing effects. So when people got ill, they would collect willow bark and brew it into a tea and drink it, which is great, except there's a small problem. So this carboxyl group is what is helping with reducing fever and pain killing and so forth. But this group right here, you can see it, they've labeled a phenolic group. This guy is also acidic. So both of these guys are acidic, and that highest acidity caused nausea and upset stomach, which when you already don't feel good, not such a great thing. I mean, it depends on how high your fever is and how bad your pain is, you might be okay with it. But a company named Bayer, might sound familiar, modified this group into another group called an ester group. Basically, they modified this so it wasn't as acidic. So this molecule became, the whole thing became less acidic. And they created a new medication. They created aspirin. So if you've taken aspirin, you have taken a version of salicylic acid. And so this isn't the only medication we have that's based off of a chemical that comes from trees or plants or insects. So sometimes we take what we have, and if there is a side effect like here, we figure out how we may be able to modify it so that the side effects aren't so bad. Right, one more functional group, and that is the esters. So you can see here what is different. It's similar to those organic acids, except the hydrogen on the hydroxyl, the OH, has been replaced by a hydrocarbon group. So this is what makes these guys not acidic. It's got a hydrocarbon group out here, so they won't be acidic. They won't be able to donate the hydrogen that's normally sitting here. And you might be going, well, okay, why do we care about the esters? Well, the thing is that these guys are super fragrant. Because of this alteration, they become very fragrant in their odor. And these are what give a lot of fruits and flowers their odor and taste. In fact, all of the ones that you see here, so rum, peaches, bananas, oranges, and pineapples, all have esters to thank for their odor and taste. In fact, we have been able to synthesize all of these as well as get them naturally. So a lot of esters we've been able to synthesize to be able to make the artificial versions of the flavorings that are pretty close, if not identical, to the natural ones, because we're basically just building the chemicals atom by atom.